I'll be discussing about another example for a multi-story building, uh, a three-story building analyzed in non-sway and sway analysis. Or for a non-sway behavior, we will only load the multi-story building with a gravity load, a symmetrical gravity load, such that it will not cause any sway. Okay. Okay, so this is our building, a three-story building, and this is the loadings applied. As you see, it's a uniform load, 5 kilonewton per meter, applied on these two members. So it's also symmetrical. So the load is symmetrical, the building is symmetrical. Okay, so we don't expect sway lateral lateral behavior, or we will neglect that. And of course, the cross section should be symmetrical and inertia. So to idealize the building, this is the node numbering. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in total, we have 16 joints. For the members, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have 16 joints and 21 members. And the length or span of the girders are 4 meters, while the columns are 3 meters. Now this is the degrees of freedom numbering if you analyze it as a sway frame. While this one below is much simpler because we will analyze it as non-sway. Therefore, the active degrees of freedom will only be rotation. Okay, so I'll show you the complete degrees of freedom here. So this is the complete degrees of freedom using beam stiffness formulation. We have 2 degrees of freedom per node. Okay, okay, 2 degrees of freedom. Now, since we will analyze it, or we will assume it as non-sway, we will neglect the lateral degrees of freedom. So therefore, the only active degrees of freedom are 4, 6, 8, 12, 14, 16, 20, 22, 24, 28, 30, 32. So all in all, we have 1, 2, 3 times 4. We have 12 unknowns in a non-sway analysis. Okay, therefore, our S matrix is 12 by 12. Okay, and these are the corresponding coding for that. Right? And our expected elastic curve is something like this. I just made it exaggerated because since the application of load is here, therefore this span here will curve like that. Okay. Now again, this is our stiffness formula. P equals SD, therefore displacement is equal to S inverse P. And using our SMAT code, this is my corresponding S matrix. So it's a 12 by 12 S matrix. And as you notice, it's a banded matrix. Okay, now as you see, my applied loads are applied in code 1, 4, 10, which corresponds to corresponds to Remember, because our code for P will also be this, right? So 1, 4, therefore uh, I have a load applied at first, degrees of freedom 4, and at the fourth, 1, 2, 3, 4, degrees of freedom 12, and at 10, which is later. So 1, 4, and 10. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the active uh, degrees of freedom wherein my load is applied, which is makes sense because this is 4, 12, 28. By the way, also 20, code 20. PF7, which is 1, 2, 3, 4, 5, 6, 7. Right? We have a moment here, a fixed end force here, also here. Okay, so that's it. So that's the code that we will require to form our S matrix. And let me share my SMAT file for that. So this is a non-sway code for non-sway frame, multi-story building. So I have here a member 21, a number of joints 16, as we counted here. Here we have 16 joints and 21 members. Therefore, this code will loop to the number of joints, and the length of our columns are 3 meters, while the length of the girders are 4 meters. And I assume a uniform cross section, therefore a uniform inertia for the length. Of course, the size of this L matrix and I matrix corresponds to the number of joints. Number of members. For the incidence, I need to define the incidence, the connecting joints. I have member 1. I'll be connecting joint 1 and 2 here. So joint 1 and 2. They will be connected. That will be member 1. Member 2 will be 2 and 3, right? Member 3 will be 3 and 4. Okay. Member 4 will be 5 and 6. Okay. As you see, that is consistent with my numbering here. Okay. Member until member 15, 16. Okay, 15, 16. For the girders, I'll be connecting node 2 and 6. So that's 2 and 6. 3 and 7 here. Oops. Okay. Okay, 3 and 7. Just this one. And as you notice, the length of the member here is already 4. 1, 2. So that's it. Okay. So this should be consistent. Okay. So that is the incidence, member incidence. So imagine that is also the same with how we label or connect beams in STAAD. For this one, this is a matrix for the constrained nodes. Okay, my constrained nodes are 1, 2, 9, 10, 7. 1, 2. This will be my reference here. That one. Right? So 1, 2. Constraint 1, 2. That means there's no displacement there. Zero displacement. 9, 10. Okay. 9, 10. 17, 18. 17, 18. And 25, 26. 25, 26. Okay. For the next, well, you know this already. This is the code to generate the stiffness matrix of each element. Okay. Here, this is a vector or a matrix that I need to customize just to check my coding. Okay. This one is the matrix that will be displaced. Remember 4, 6, 8. So because we are analyzing in a non-sway frame, so 4, 6, 8, okay, 12, 14, 16, okay, 20, rotation in 22, rotation 24, so on and so forth. 28, 30, 30. Okay? And so remember, the BB matrix is the destination, right, on our 12 by 12 S matrix, right? So remember, for example, here for the member 1, the only required uh, the unknown displacement is at code 4, so which is located at the first element. Okay, so on and so forth. For member 2, code required is 4 and 6, which is located in the first and second element, right? And remember, this is our code numbering for the S matrix. Okay. Next is this one is the transformation matrix. Remember, if your element is a column, this will be your transformation matrix. If it's a beam, this one is your transformation matrix. That's why I looked here from member 1 to 12. The transformation matrix is this. And for 13 to the 21st member, this is the transformation matrix. Remember, these are the column and this is the beam. That's why, okay, so that's why you should have a prepared picture or a diagram indicating the member numbers. So I have, that means member 1 to 12 are all columns. So you should organize your code such that the first 12 or all the columns will be numbered first, while member 13 all the way to 21 are all beams. Okay. And this code will get the global stiffness matrix. And finally, this is our BU and BB matrix. Therefore, in this code, the BU and BB matrix is automated, except on the red portion above. I need to check if the code generated correct, and other than that, it's all automated. Now this one, remember, you need to set a null matrix of an S matrix. Here I need, since the unknown displacements are quite large, it's a 12 by 1 matrix. So I need to prepare a null matrix of 12 by 1 first, and then I'll just have to insert a value of p of um, of a non-zero value of element inside the P matrix, which are the loads. Okay, remember, I have, for example, I check. Okay, remember, we have a load here, right? Therefore, this uniform load, will cause a force on 4, right? On the first and the fourth and 7 and 10. Okay? Which I explained earlier. And remember, how do you get these values? Since since our load is a uniform load, so the formula is WL squared over 12, the fixed end force. Okay, so once P vector and S matrix are known, we can now generate the displacements. Again, these are the QF forces, and this code will automate the generation of the member forces. After you get the displacement multiplied to the global stiffness matrix of each element, and then add to each QF vector for each element, and this is what we got. So these are all the member forces. And for example, to verify, let's verify Q1. So this is our STAAD. Okay, no sway. Okay, so this is our STAAD file. So this is the 3-story, 3-bay non-sway frame. So after running the analysis, double click to get the member forces. So for bending, I have 1.3 and 2.85. And as you see here, for Q sub 1, about 1 point bending, right? So 1.4 and 2.89. Okay. For the shear, I have 1.4 both ends, so which is almost equal to our SPAN, 1.4. Okay, remember, in STAAD, it's not using only a beam stiffness formulation. It's using a full 3D. No, it's using a full 3D space frame stiffness matrix. Okay, and as you notice, we just use a beam stiffness formulation, and we almost get the same answer, because that means our assumption of a non-sway frame, of neglecting the actual stiffness, and actual deformation, of course, and other degrees of freedom is still valid. Okay, so therefore you can analyze a multi-story building using just a stiffness matrix formulation of a beam, uh, as long as these assumptions are still valid. For example, member 4. What is our member 4? According to our, this is our member 4, the second column. So second column, I'll check the second column here. So my bending is again 1 and 2, 1.18 and 2.5. So I'm getting 1.2 and 2.5, right? For the shear, I'm getting 1.23 on both ends. So 1.28. Okay, not quite quite close. For Q7, what is Q7? Third column. Maybe let's check the fourth column. Q's 10, member 10, which is Q sub 10. Since it's symmetrical, so you're bending 1.3, 2.85, yeah, 1.4, 2.89, and for the shear, 1.4 both ends, 1.4. Let's check on the loaded beam here. This is member what? According to our code, member 13. So I'm getting Q13, which is this one. My bending is 9.9 and 10.10. So very close, 9.9, 10.10 here. Okay. For the sorry, that's the shear. 9.9, 10.10. For the bending, it's 5.4 and 5.8, which is very close, right? 5.4, 5.8. Okay, so that means this is good. This is correct. Okay, so that's it. Using SMAT, you can analyze a multi-story building non-sway frame.